Hey guys, Mr. Brewer back here. Today's lesson give you some strategies on how to become a little more efficient at balancing. So when we use some strategies, it gives you a little bit better skills with this. So let's give you some quickie reminders about what balancing is about by having you take a look at some of the notes that we've recently covered, and we'll just kind of scroll through that. Okay, why don't we get down to what today's lesson is about then? So specifically, I'm going to work with teaching you a few strategies. And let's put up here what those two strategies relate to so we can get down to business. So specifically, we're going to look at strategies for two different kinds of reactions. Actually, not really two different kinds. Reactions that contain polyatomic ions and reactions that we would call combustion reactions. So what we're speaking about are some strategies that give you a little bit better skills with this. So again, this is the purpose of today's lesson right here. Looking for a strategy to balance an equation if it contains a polyatomic ion or if it's a combustion reaction. So let's start with equations that contain polyatomic ions. So here is an equation, and we're going to see that it has what we call polyatomic ions, ions that are made up of more than one atom. So PO4 is what we call polyatomic. We see it on both sides. So that's what we want to kind of train our eye for when we start here. We want to look, does each side of the equation contain the same polyatomic ion? And if it does, that's going to help us balance. So PO4 on the left side, PO4 on the right side. NO3 on the left side, NO3 on the right side. What I like to say is we want to balance it like it's a unit up here. So we're going to keep it together as being one thing. Notice PO4 is not in parentheses on the left side, but it is on the right side. So all this really indicates is that there's two PO4 or phosphate on the right, but only one PO4 on the left. So we're going to use our inventory strategy like we have in the past. And that inventory strategy is going to help us reveal the coefficients. So if we were to get started with this, right, what I reveal here is really just a way to think about each particle. Na3PO4 would be this large particle here, MgNO32, this large particle, NaNO3, Mg3PO42. So this just helps us visualize a little bit. So what we're going to notice is we're going to notice that the PO4 is a particle that is actually a large chunk. So we're going to take our inventory. We start our inventory with what participates in the reaction. So our inventory is going to include polyatomic ions, in this case, ions made of more than one atom. So sodium's an element that participates. So we're going to put that in our inventory. Phosphate, that's this big chunk, 1P and 4 O's, that's part of Na3PO4. So we're going to put that in our inventory as a unit. We're going to keep it together as a unit. So the next thing that participates would be magnesium, kind of this light pink color particle. And the next particle that participates would be nitrate, NO3. So our nitrate would be this green surrounded by 3 reds. So we see, this says MgNO32. We see 2 pieces of this chunk in this particular particle over here. So the way that we start this is we sort of take an inventory of what we have. So when we go to take our inventory, that allows us to write down quantities. So if we were to start with sodium's inventory, right, the inventory for sodium reveals a very specific quantity. In this case, it reveals on the left side 3 NAs. So we'll put a 3 there. On the right side, where we find sodium, there's only 1. So we've inventoried sodium. Let's inventory PO4, phosphate. Notice it's not in parentheses. So on the left side, there's 1. PO4 is in parentheses on the right side. So our inventory for product side says there's 2. Let's inventory magnesium. On the left side, no number associated. So there's 1 magnesium. On the right side, there's a 3. So there's 3 there. Let's go to our nitrate, or NO3. On the left side, there are 2. On the right side, there's only 1. Notice it's not in parentheses. So nothing's balanced here. Na is not balanced, PO4 is not, Mg is not, NO3 is not. So we're going to choose coefficients to try to make this work. So we're going to choose some coefficients. So it doesn't really matter where you start. Some people like to say that there is a method to the madness about where to start, but one thing you can realize is you can always start over if you're going back and forth and you get led to a dead end. So what you'd want to do then is start in a new place. So I don't know, I think I'm going to start here with the sodium quantity, the phosphate, the PO4 quantity. So PO4 says 2 on the right side, but we know there's only 1 on the left side. So the only way we can fix that is with a coefficient. So the coefficient we choose to put here, we need to double the amount of PO4 that was present, because right now there's only 1 PO4 on the reactant side. So coefficient of 2 doubles that. Now we have 2 PO4s on the left side. So this 1 is no longer a 1, it's now a 2. Now our PO4 is balanced. However, what this did is this changed the sodium amount. The original sodium amount is now doubled. So now instead of there being 3 sodium on the left side, now there are 6. So that means over here on the right side for sodium, that's going to have to be corrected, because wherever we see sodium on the right side, there's only 1 right now. So part of our thinking about this relates to the idea that we just made 2 particles of this. So by making 2 particles of Na3PO4, it created 6 sodium on the left side. So that means 6 sodium need to be placed on the right side. So that means we need to choose a coefficient in front of sodium over here on the right side, because there's really only 1 right now. So our coefficient that we would like to choose, we'd like to choose a value of 6 for that. That multiplies the sodium amount by 6, and this 1 now changes to a 6. So we've changed our sodium amount to 6. Hey, look, our sodium's balanced now. However, what this also did is this multiplied the NO3 amount that used to be here on the right side. On the right side, there was 1 nitrate. Well, that just changed this. It's no longer 1. Now it's a 6, because 6 times the 1 that were already there creates 6. So we now know that we would need 6 nitrate on the left side. Right now we only have 2. Our 2 right here indicates that. So we're thinking about a multiplier, a coefficient that we would put here to fix that. Well, the coefficient 3 times the 2 that's back there already creates the 6 nitrates that we wanted on the reactant side. So now we have our 6 nitrates. So 6 nitrates, now nitrate is balanced, or NO3. So the only thing we need to check now is our magnesium amount. If we look what we just did, we just tripled the amount of magnesium that was present. There was 1, but now On the reactant side, there's no longer one. Now there are 3 because we chose a coefficient of 3. If I go back over to the product side and look, this is where this original 3 came from here on the right side of magnesium. So this is now a balanced equation, revealing that everything is now balanced with coefficients. So our coefficients become 2, 3, 6, 1. So 2, 3, 6, and 1. If we look at what the visual up top shows us, 2 particles of Na3PO4, 3 particles of MgNO32, 6 particles of NaNO3, and 1 of Mg3PO4. By keeping the polyatomic ions together as units, it helps us balance an equation with a little bit more efficiency. So whenever we notice a polyatomic ion, look to see if it's also on the opposite side, and that will allow us to set up our inventory. So our coefficients 2, 3, 6, 1 create a balanced equation here. Let's clear our drawing here, and let's start with a new equation. So here's an equation we're going to keep an inventory of. So we see, oh, polyatomic ion, look at that, SO4, SO4. SO4 is in parentheses over here with a 3, not in parentheses over here, but sulfate or SO4 is on both sides. We're going to keep that as a unit, keep it together. So let's take our inventory: calcium, aluminum, and SO4, our polyatomic ion. Next thing that we'll do is now we will put quantities in our inventory. 1 calcium on the left side, 1 calcium on the right side. Calcium, calcium. Calcium's already balanced. So let's look at aluminum. Aluminum on the left side, reactant, there's 2. On the right side, aluminum, there's no subscript here, so there's 1. Aluminum's not balanced. Sulfate, SO4 is in parentheses on the left side. So reactant side sulfate or SO4 is 3. Product side, however, there's only 1. It's not in parentheses. So calcium is the only thing that's balanced. So we're going to choose coefficients to begin to balance this. So maybe a good place to start would be maybe with our SO4 ion. Notice there's 3 SO4s on the left, but only 1 on the right. We fix that with coefficients. So we want some coefficient in front of this chemical that will triple the amount of SO4, while 3 causes that to triple. So we get 3 SO4s now on the product side. So our inventory reflects that now. Our sulfate is balanced. Recall what this does though, however, this triples the amount of calcium. So now on the product side, there's no longer 1 calcium, there's actually 3. So what we want to do is go back over to the reactant side, choose a coefficient to triple that amount, coefficient 3. Our inventory would now say there's 3 calcium as reactant and 3 calcium as product. So the only thing that is not balanced now is our aluminum. So we'll just double check what we can do here. 2 aluminum on the reactant side, 1 on the product side. So that means we're going to come over here to our product side and we want to look to double that amount of aluminum. Well, the coefficient of 2 would cause that to double. And we end up with 2 aluminum on reactant side, 2 aluminum on product side. So our balanced equation reveals coefficients. Our coefficients of 3, 1, 2, 3, right? 3, 1, 2, 3. That becomes the balanced equation for this particular skeleton equation. So we can do this again with another example here. Fix your eye on the polyatomic ions that you see on each side. You're going to keep them together as units. So let's take our inventory. So iron, Fe, ClO3 is the ion called chlorate. I see it on the left side. I see it on the right side. Let's keep it as a unit. K, or potassium, the polyatomic ion called carbonate, CO3. So we have 2 polyatomic ions in this case. Let's begin to take our numerical inventory. iron on the reactant side. There's no number here, so there's 1 iron. On the product side, there are 2. ClO3, well, it's in parentheses, so on the reactant side, there are 3 of them. On the product side, not in parentheses, so there's only 1. K, well, on the left side, the 2 subscript belongs to K. On the right side, no number after K, so there's 1. So that's not balanced either. And our last ion to balance, carbonate, CO3. On the left side, carbonate's not in parentheses, so no parentheses around it. That means there's a single carbonate ion. Over here on the product side, however, there are 3, since CO3 is found in parentheses. So when I look at this, none of the ions are balanced. So that means what we're going to need to do is choose coefficients to begin balancing. Again, it doesn't really matter where you choose to start. And if you get stuck, I would erase, start over, start in a different place. So I'm going to start maybe with carbonate, CO3. So for CO3, what I see on the right side is I see there are 3 of them, right? 3 CO3s on the right side, but only 1 on the left side. So we need some number here that's going to triple the amount of CO3. Well, the value 3 causes that. So that changes the amount of carbonate for CO3. It makes it 6. So carbonate is now balanced. However, what this does is this triples the amount of K that used to be there. There used to be 2. So our 2 is no longer valid. Now there are 6K because 3 times 2 changes that quantity. So 6K on the left side, now we need 6K on the right side. So we're going to need to choose a coefficient to create that to make it 6 times more than what used to be there. Well, there used to be 1K on the right side. So the coefficient we're going to choose is 6, right? So now we end up with 6Ks on the right side. So our coefficient of 6 balances our K, or our potassium. We just go back and look at what this did to our ClO3s. There was 1 ClO3 on the right side. Remember 1 over here, it wasn't in parentheses, but now this made it 6 times more than what it used to be. So now it's no longer 1, now it's 6. So that means we're going to need some coefficient over here on the left side to take that 3 and multiply it to create the quantity of 6. So the coefficient that would do that would be a 2. 2 times the 3 that's already there, right? That 3 is no longer valid. Now it's 6. So our ClO3 is balanced. Just pay attention to what this just did to the iron. There was 1 iron on the left side, as we indicated in our inventory. That 1's no longer valid because we just doubled that amount. Oh, look at that. 2 iron, 6 ClO3s, 6 Ks, 6 CO3s. Our inventory is now balanced. Our coefficients to get the balanced equation, 2, 3, 1, and 6. So 2, 3, 1, 6 creates the balanced equation for this particular skeleton equation. Let's clear the drawing here so we can take a look at this last example with a little bit more clarity. Okay, so maybe you should pause the video and see if you could take a successful inventory and see where you end up with balancing. So as you take your inventory or took your inventory, you should have started with magnesium. NO3 is found on both sides, so NO3, called nitrate. Barium, found on both sides. The polyatomic ion phosphate, found on both sides. So we have our inventory. These are the things that we need to keep track of. Let's add some numerical values to them. Mg on the left side, there's 1. On the right side over here, there are 3. So our inventory shows magnesium's not balanced. NO3 on the left side shows that there are 2 of them because it's in parentheses. On the right side, it also shows 2. So our nitrate is balanced. Barium on the left side, it shows 3. On the right side, it only shows 1. And phosphate on the left side, our reactant side, we show 2. And on our product side, we also show 2. So it looks like our barium and our magnesium are not balanced, but everything else is. That may change. So we're going to look for coefficients to fix this. So let's start maybe starting with the magnesium in this case. So we want to choose a coefficient that's going to create 3 magnesium. So the amount on the right side, magnesium with 3 here, is equal to the amount on the left side. So the coefficient that we would need to triple that amount of magnesium would be 3. That means the 1 magnesium that used to be there is no longer valid. It's now 3. So magnesium is now balanced. Pay attention to what this did to the nitrate or the NO3 ion. It just made 3 times more than what used to be there. Well, there used to be 2 nitrate ions. That's no longer valid. 3 times that 2 now makes 6. So we now have 6 nitrate ions on the reactant side. That means we're going to need 6 nitrate ions on the product side. Well, we started out with only 2. So we know we're going to have to put a coefficient multiplier in here to create 6 nitrate. Well, that means the value 3 will also go here. 3 times the 2 behind here creates 6 nitrate. So the 2 that used to be there is no longer valid. Now there are 6. Now our nitrate, or NO3, is balanced. What we need to notice is this changed the barium amount from the original 1 on the product side to, it tripled it to 3. So there used to be 1 barium on the product side. Now there are 3. Look at that. What that did is that balanced the barium amount. So it looks to me like everything is balanced in our inventory. 3 magnesium, 6 nitrate, 3 barium, and 2 phosphate. So this is what we look for. We look for polyatomic ions. We keep them together as a unit. And this is a really powerful strategy. It makes balancing much more efficient when we recognize polyatomic ions. So our coefficients, 3, 1, 1, 3, 3, 1, 1, 3, balance this equation. Let's clear our drawing and let's take a look at our second strategy for today. The second strategy is going to relate to a reaction that we call combustion reactions, also a very powerful strategy. So we notice this is a combustion reaction, has oxygen as a reactant. What this says we should do is we should balance the O atoms last. So when we take our inventory, we'll look at what elements are present, carbon, hydrogen, and oxygen on each side. And we're going to balance the O atoms as the last thing when we take our inventory. So what we're going to do is we're going to apply our numerical amounts. Carbon on the left side, there are 3. On the right side, however, there's only 1. So our inventory says carbon's not balanced. Hydrogen on the left side, there are 8. Over here on our right side, there are only 2. We know hydrogen's not balanced. Oxygen on the left side, there are 2. Be careful over here on the right side. Oxygen's in 2 places, so we need the sum total. 2 from CO2 and 1 from H2O. 2 plus that 1 make 3. So we need to look in 2 places because oxygen appears in 2 places. That's why we're going to save it for last. Okay, so let's begin with our carbon because we know our carbon's not balanced. So we need to choose a coefficient that's going to create the same quantity of carbon on each side. Well, since there's 3 on the left side, but only 1 on the right side, coefficient of 3 makes sense here to balance the carbon amount. The 1 that used to be there is no longer valid. Now it's 3. Carbon's balanced. Again, we're going to ignore what that does to oxygen. We'll come back to oxygen. Let's look at hydrogen next. 8 on the left side, only 2 on the right side. So multiply our coefficient 4 times 2, right? The 2 that used to be there is no longer valid. We just multiplied it by 4. Now hydrogen is balanced. So carbon and hydrogen are now balanced. Now we can take inventory of oxygen. New inventory for oxygen because we just put numbers here. So on the left side, the oxygen value is still 2, but on the right side, it's no longer 2. So we're going to change this value. 3 times 2 for carbon dioxide, right? There are 6 oxygen. 4 times 1 for water, there are 4 from water. 6 plus 4, now there's 10 oxygen on the product side. That means we need 10 oxygen on the reactant side. So we need a multiplier, a coefficient. Well, 5 becomes the multiplier. So we change multiplier to 5, and that creates the value that we want. So what we end up with is we end up with coefficients of 1, 5, 3, 4, create the balanced equation. If we go back and look at our inventory, it looks like I didn't quite fix this inventory here, but the reason this is no longer 2 on the oxygen side is 5 times 2 made the 10 that we wanted for our reactant. Okay, let's see. In red here, you see there's a strategy. It says you may need to consider a coefficient value, including a decimal in some cases. Well, this might be a first example where we actually see that that becomes a challenge or a problem. So let's begin to take our inventory. We have C's, H's, and O's. So as we look at our C's, our H's, and our O's, we're going to notice that we have an inventory that tells us a little bit about quantity of each. So we can apply some numerical values, and applying numerical values to each of these tells us what is and what is not balanced. So that'd be a good place to start. Okay, so we'll begin to apply numerical values. For carbon, we see 4 on the left side. Over on the right side where carbon is, there's only 1. So our inventory says that's not balanced. Hydrogen, 10 on the left side. On the right side, we only see 2. So our inventory says hydrogen's not balanced. Oxygen on the left side, 2 oxygen. Careful, oxygen's found in 2 places on the right side. 2 from CO2, 1 from H2O. So there are a total of 3 oxygen on the right side. So nothing's balanced right now. Remember, the strategy is save oxygen atoms for the last thing to balance. So let's begin balancing our carbon. Well, what we wish to do then is put a 4 here for carbon, because there was 1 carbon on the product side. We want to quadruple that amount. We want to make it 4. So multiplier of 4 fixes carbon. Ignore what that does to oxygen. We're coming back to that later. Okay, let's look at our hydrogen now. Hydrogen 10 on the left side, but only 2 on the right side. There's only 1 multiplier that will create 10. That's the value 5. So 2 is no longer valid because we just multiplied that by 5. So now hydrogen is also balanced. 5 times 2 made the 10 we wanted. Now we're going to look at our oxygen. Our inventory on the left side says there's still 2 O's, but now on the right side, oxygen's found in 2 places. 8 from CO2, so the value 8, ooh, that's a crummy looking 8, isn't it? So 8 from CO2 and 5 from water. Well, 8 plus 5, that gives us the total now on the right side. There's no longer 3 because those coefficients change those amounts. So there's 13 on the right side. So here's where this strategy says we might want to choose a decimal in some cases. There's no whole number I'll be able to put in front of here that would multiply 2, or that would be multiplied by 2 that would create 13. So it's almost like, what number could we multiply 2 by to create 13? Or maybe a different way of thinking about that would be the reverse. If somebody had $13 and they were going to split it with a friend, well, wouldn't each person be getting a very specific amount then? So let's kind of reveal what we did with coefficients, 4 and 5. Well, if each person needed to get an equal amount of $13, each person would be getting $6.50 because 6.5 times 2 creates the 13 that we wish to have. Let me clear the drawing here a little bit. So 13 is the total value that we wanted to get. Well, we want to get whole numbers. So in order to get rid of this decimal version, simple way to get rid of that decimal version would be to multiply it by 2, double it. So when I double that amount, that creates 13. But anytime that I multiply a coefficient by a value, every other coefficient that we've already written must be multiplied by that value. So even though we didn't write a coefficient over here, remember when there's no coefficient, it means value 2. So 1 times 2 makes 2. We've already doubled this amount. We doubled this amount. So 2 C4H10s, 13 O2s. We have to double the amount of CO2. It becomes 8. We have to double the amount of water. It becomes 10. If we go back and take an inventory, we're going to find out that they're balanced now. So what we're going to see on each side, 2 times 4 for carbon, we're going to see 8 carbon. I see 8 carbon, 8 times 1. So for hydrogen, 2 times 10, right? I see 20 hydrogen on the left side. Look at this, 10 times 2, 20 on the right side. Oxygen, 13 times 2, well, that's 26. Well, how do we get 26 on the right side? 8 times 2 is 16, plus the 10 times 1 for water here. There's like an assumed 1 back here. So 16 plus 10, 26. So everything is balanced with this strategy where we had to incorporate a decimal value. Let's see if we can't get you to try this. So here is an example for you to try. Take your inventory, pause the video, and see if you can arrive at an answer. So hopefully in your inventory, you included these 3 elements, carbon, hydrogen, and oxygen. You began to add numerical values to your inventory. Over here on the left side for carbon, you said 8. On the right side, you said 1. For hydrogen, on the left side, you said 18 for reactant side. For product side, hydrogen, look, there's only 2. We know that's not balanced. Oxygen on the left side, 2. Oxygen on the right side, 1 from CO and 1 from water. Oh, look, oxygen's balanced. That might change. Okay. So we're going to balance by adding coefficients. Again, it's a combustion reaction. Save oxygen for last. So what we're going to do, we're going to balance our carbon, multiply our coefficient to get 8 carbon on the right side, multiplier of 8. So we make 8 carbon now. Carbon's now balanced. Hydrogen, 18 on the left side. We need a multiplier to multiply by 2. That would create 18 on the right side. So that means a value of 9. So now that creates 18 on the right side. Now we can go back and deal with oxygen. Let's change the color here. Let's make pink. So on the left side, we see there's still 2 O's, but we just changed the amount of O on the right side. We got 8 times 1 from CO, which means 8 from CO. And 9 times 1 for water, which means 9 from water. 8 plus 9, wow, now we got 17 oxygen on the right side. So we're going to need a multiplier in front here. So let's reveal what we've done, right? We've chosen 8, we've chosen 9. Some multiplier in front of 2, that's going to create 17 oxygen. So that's kind of like $17 being split up between 2 people. Well, we would know each person would get $8.50 then, or 8.5. What we want to do is we want to get rid of that decimal value by multiplying it by 2. 8.5 times 2 makes 17. Every other coefficient needs to be multiplied by 2 because I multiplied one of the coefficients by 2. So the 1 that used to be here becomes a 2 because I multiply it by 2. The 8 that used to be here becomes a 16. The 9 that used to be here becomes an 18. This is a very powerful strategy, and you'll want to try to only apply it in the case where you have combustion reactions. And recall how you know if you have a combustion reaction, O2 as a reactant. So where we see O2 on the reactant side, that's when we're going to think about applying this strategy. So I hope you found today's lesson useful. Very specific strategies for kinds of equations. One called a combustion reaction, and another type when we have what we call a polyatomic ions. So if we go back to our goals, when do we apply these strategies? Well, we would apply these strategies only in very specific cases. And that's what I'd like you to begin to train your eye for. When do we use this? Well, we use this in cases when we have polyatomic ions present. So polyatomic ions, you're going to keep them as a unit. That might be something like NO3, right? Ion made of more than one atom. Combustion reactions, when you see on the reactant side oxygen, right, what you're going to do is you're going to balance oxygen last. So until the next time, I bid you peace, and I hope that you found today's lesson useful and that you'll take the time that you need to wrestle with the idea today. So please feel free to shoot me any questions that you have as you do your practice work. And I think if you try to keep up with this on a day-to-day basis, we're going to find that we learn and grow a little bit each day. So take care until the next time. Peace out.